Hello, in this video I'd like to talk about the weak monadic second-order theory of two successors. So if you remember back to my regular languages and model theory series, we used finite state automata on ordinary words in order to reason about the weak monadic second-order theory of one successor. Let me remind you what that looked like. So the weak monadic second-order theory of one successor was the study of the natural numbers with its one successor operation, the +1 operation, and finite sets of natural numbers. So the weak monadic second-order part refers to the fact that in addition to studying the natural numbers with successor and their properties, we're also studying what we can say logically when we also involve finite sets into our language. And the key idea here was that there was some sort of correspondence that we could take advantage of between finite sets of natural numbers and words. If we had a particular word, we could encode it not as a single finite set, but as a finite collection of finite sets, specifically one finite set for every character in our alphabet. And we just turned the word, we looked at each character, and we looked at the set of positions within the word where that character appeared. This allowed us to turn a single word into some sort of finite collection of sets. And not just any finite, it's bounded. It's a specific number, usually 2. We usually have just 2 characters in our alphabets. So it was usually just turning a single word into 2 finite sets. And that's perfectly reasonable to do in terms of first-order logic. If we have one variable representing a word and we turn it into 2 variables representing the set of positions where the character A appears and the set of positions where the character B appears, that simply like doubles the size of the formula, right? Every variable representing that word gets replaced by 2 variables. We have to handle them, but that's perfectly fine. It just doubles the size of the formula. It's still a first-order logical formula. We haven't done anything beyond the capacity of first-order logic to reason about. And if we had a finite set of natural numbers, we could turn it into what I call a characteristic word. It's a word that has B's in positions which are exactly the numbers in that particular set. And again, the correspondence here is a little bit loose. We want to say that the last character of these words is a B, so that they don't have any like unnecessary trailing A's at the end of the word. But fortunately, that's something that we can talk about in the corresponding first-order logic, so we don't need to worry about that. And the idea was that we could translate back and forth between the logic of words, which really was talking about automata on words, and the logic of finite sets of natural numbers, specifically the weak monadic second-order theory of one successor. We could translate back and forth and use our understanding of automata in order to study weak S1S. So now we're interested in studying the weak monadic second-order theory of two successors. And I'm going to name those successors Successor R and Successor L, and we'll see why in just a moment. But just like how we could generate the natural numbers starting from a single base, 0, and applying the successor operation as many times as we wanted, we can generate words on the characters R and L by starting from a single base, the empty word, and applying the successor R, the tack an R onto the end of a word operation, and successor L, the tack an L onto the end of a word operation. And this is what it means to study the theory of two successors, studying this structure here. Of course, we're not just studying any theory of two successors, we're studying the weak monadic second-order theory of two successors. So again, second order means that we're studying either relations or functions or operations on these first order objects, these words here. And monadic means that we're just studying sets of words. We're just studying sets of these first-order objects. And then weak means actually we're just studying finite sets. And just like how we could translate back and forth between finite sets of natural numbers and words, we can translate back and forth between finite sets of words on R and L and tree words. So the key idea is that positions within a tree word, within a binary tree, correspond to words on the characters R and L. And what that means is that we can translate a tree word into the set of positions where particular characters appear. Let's do an example. So suppose that we have a tree word that looks like this. Then we can turn it into two sets, a set A and a set B. A is going to be the set of positions, or rather the set of words that represent those positions, where the character A appears, and the set B is going to be the set of positions where the character B appears. In particular, the way that we represent a position within a binary tree is in terms of the sequence of operations of going to the left child or going to the right child that we have to take starting from the root in order to get to that position. So if we're trying to get to the root, we don't have to go anywhere, and so we have an empty sequence of operations. And so to represent the fact that the character A is at the root, we want to include the empty word within our set A. In order to represent this position here, to get there from the root, we need to go to the right child once. And so we can represent this position by the word that's just the character R. Again, it describes the sequence of steps of either going to the left child or going to the right child that we need to take in order to get there. And so to represent the fact that this node has an A associated to it, we put the word R in the set A. To get to this position from the root, we go to the left child twice, and so that corresponds to the word LL, and so we're going to toss the word LL into our set A, and in order to get to this node, we go to the right child twice, and so this node is represented by the word RR, and so we put RR into the set A. Similarly for B, in order to, for instance, get to this node here, we need to go to the left child twice and then to the right child, and so that corresponds to the word LLR being in the set representing the set of positions where the character B appears. So we can represent a tree word on the characters A and B as a pair of second-order elements within weak S2S, a pair of finite sets of words on the characters R and L. And similarly to the case of weak S1S, if we have a set, we can translate it back. If we have a set of words on R and L, we can translate it into a tree word, which is a B at positions X, which appear in the set, just like we did over here. It's not a reverse of this translation, but it's a good enough translation back and forth that we can translate the logic back and forth. Suppose that we had the second order element, the finite set of words on R and L that contained the empty word, the word R, and the word LR. We could represent it as a tree word as follows. We're going to want to put a B at the root because the empty word corresponds to the position of the root. We're going to want to put a B at the position corresponding to the right child of the root. So we'll add in a right child to the root and we'll put a B there. And then we're also going to want to put a b at the position given by the right child of the left child of the root. And in order to do that, we're going to have to add in a left child to the root. This is not, the word L is not in our set, and so we're not going to want to put a B here. And so I guess we'll just put an A there. And then we are going to want to put a B at this position here, which corresponds to the word LR, right? Going to the left and then going to the right. And again, just like in the case of weak S1S, we want everything to end with B's. We don't want there to be extra A's kind of dangling off the end of this representation here. And because we have this translation back and forth between tree words and sets of words on the characters R and L, the second order elements of weak S2S, we can translate back and forth between tree automata, which reason about these tree words, and logical formulas in weak S2S, which reason about these finite sets of words. And of course, I'm interested in studying this particular logic. What sorts of things can we express in this logic? Well, what sorts of things can we express with tree automata? What sorts of sentences in this logic are true? Well, we can determine that by translating those sentences into tree automata and asking what happens with those. What sorts of structures behave logically like this particular structure? Well, what sorts of structures can we make sense of the notion of tree automata on? This is a very fruitful conversion back and forth, just like the conversion back and forth between ordinary automata and logical formulas in weak S1S was very fruitful. So let me take a moment to talk about what we can do with logical formulas in weak S2S. So the weak monadic second-order theory of two successors is the theory of, and again, I want to think of this as a two-typed structure. We have objects of the first type, which are just words on the characters R and L, and we have objects of the second type, which are just going to be finite sets of words on the characters R and L. Here I'm using the calligraphic F in place of the calligraphic P to represent the finite subsets of this language here. And then we have the operations successor L and successor R on words, and we have containment between words and finite sets. And we can build up a formula in this theory as follows. We start off with terms. These are going to be variables. I'll use lowercase variables to represent words and uppercase variables to represent sets. And if we have a term, we can also talk about the successor left of that term or the successor right of that term. We can build up terms in that way. And then once we have our terms, we can put them together to create atomic formulas. If we have two first-order terms, we can create the formula that says that they're equal, that they represent the same word. If we have two second-order terms, we can say that they represent the same set. Or if we have a first-order term and a second-order term, we can say that the first one represents a word that's in the second one as a set. So we can use these to build up an atomic formula as follows. Let's start with a variable lowercase x, which represents a word. So we can take its successor left, and then we can take the, let's say, successor right of that, because this is a term, so successor right of that is also a term. And then we can say that this term here, being a first-order term, is within, let's say, a capital Y, which represents a second-order term. So this expresses some sort of relationship between the word x and the set y. Very often when we're reasoning about what we can say in weak S2S, just like we did in weak S1S, we're actually going to want to take this formula and pull it apart and by relationalizing it. We had three things going on in this formula here. We had a successor right operation, a successor left operation, and a containment relation. And we'd actually like to be able to split all of those apart. And we can do that with a formula like this. There exists a z and a w, intermediate values, where z is the successor left of x. It's going to represent this term here. W is the successor right of z, so it's going to represent this term here, right? The successor right of the thing that we said z was. And then finally, we're going to want to say that w is in y. And by doing that, the only types of atomic formulas that we really need to reason about, instead of having to reason about lots of nesting, lots of complicated things going on, even in an atomic formula, we can break the atomic formula apart. It's a more complicated formula here, but the individual pieces are much simpler. And we're just combining them with ands and there exists, which we're going to need to reason about anyway. So this is the process of relationalization that we made a whole bunch of use of in the regular languages and model theory series. So we have our atomic formulas, and again, we can focus our attention on atomic formulas where there's only one thing happening in each atomic formula, not complicated atomic formulas like this. And then we combine those atomic formulas together using Boolean operations, so and, or, not, and optionally things like implies and if and only if, which are really just fancy ways of combining ands, ors, and nots. And quantifiers. And we have two types of quantifiers because we have two types of objects, two types of variables. We can say for every word x, or there exists a word x, or we can also say for every set x, or there exists a set x. And this is it. This is the extent of our language. This is all of the pieces that we have that we can put together to create formulas within weak S2S. So let me take a moment and look at some examples of what we can do in weak S2S. Just like how in weak S1S we found it very useful to talk about downwards closed sets, it's also helpful to talk about prefixed closed sets of words. These are sets of words where anytime a particular word is in the set, any prefix of the word, any initial segment of the word, is also going to be in the set. And we can express this in the language of weak S2S as follows. For any word y, if the successor left of y is in x, if y with an L on the end is in x, then the word y also has to be in x. And if y with an r tacked onto the end is in x, then y also has to be in x. So suppose that we know that the word RLLR is in our prefix closed set x. Then because the word RLL with an r tacked onto the end is in x, that tells us that RLL by itself also has to be in x. And now because RL with an L tacked onto the end is in x, RL by itself has to be in x. And so we can see that because the word RLLR has to be in x, one of its prefixes, RL, also has to be in x. And all of its prefixes have to be in x. We know that RLL is in x. We can also prove that R by itself has to be in x, and the empty word, which is a prefix of everything, also has to be in x. Another way of looking at the prefix closed sets, if we think about this in terms of positions in trees, these are going to be sets where if we have a left child or a right child of a node in the set, then its parent also has to be in the set. And so what that means is that the set looks like a tree, right? One of the criteria for a tree, when we look at the nodes that are contained in the tree, anytime a node is contained in the tree, its parent also has to be in the tree. And that's exactly what this is expressing here when we're talking about words of L's and R's in terms of positions within this tree. We can also express that a set of positions is sibling-free. That is, if the left child of a node is in the set, then the right child of the parent node is not in the set, and vice versa. We can express this as follows. For any node y, for any parent y, it's either the case that its left child is not in X or its right child is not in X. We can't have both. We can't have both the left child and the right child in X. This set is free of siblings. So for instance, this position here, RL, and this position here, RR, can't both be in the set because they are siblings of each other. And if we combine these two criteria, a set being both prefix closed and sibling free, if it's prefix closed, it's going to look like a tree, and if it's sibling free, it's not going to have any branching, it's not going to have any splitting in the tree. And in particular, that means that our set X represents a branch through a tree. It represents the set of positions of nodes that form a branch within some tree if it's both prefix closed and sibling free. So this language can actually say a fair number of things. And just like how we could use downwards closed sets to define some sort of ordering, we can use prefix closed sets to define some sort of ordering. In particular, we could talk about a node being an ancestor of another node if every prefix closed set containing one of them also necessarily has to contain the other. That means that one node is above somewhere the other node, if any tree containing the lower node also has to necessarily contain the higher node. And again, just like in the case of weak S1S, we can actually express the operation of deterministic leaf-to-root binary tree automata in this particular language here. So just like how we can represent a tree word on the characters A and B as two sets representing the locations of A's and B's, we can represent the run of a tree automaton. Remember that a run is just a tree word on the alphabet of the states of the automaton, right? We're associating a state to each node of the same tree. And so we can encode these runs as a set for every state of the positions where that state appears. So given the sets that encode a particular tree word input to our automaton, does there exist sets that encode the run, the association of states to each of the nodes, that satisfy the following properties? We're going to want to associate a state to every position in our tree. The positions in our tree are given by A union B, right? Those are just positions where A appears and positions where B appears. Well, okay, that's all of the positions. And then we want to associate one state to each of those positions, and that's going to be the xi that contains that particular position. So the xi's are going to have to be disjoint, and we're going to want their union to be the whole tree, A union B. We're going to want it to be the case that we associate some root state to the root. The root is given by position epsilon, the empty word, and so we want the empty word to be in some xi for some I which represents a final state, a root state. So we want it to be the case that for every node in our tree, based on the symbol that's associated to that node, right? Y is in A indicates that we've associated the symbol A to the node Y, and Y is in B means that the symbol B is associated to the node Y. And based on which states we wound up associating to the left and right children of Y. And it's worth noting, if Y doesn't have a left child in the tree, then none of these are going to be true, right? The xi's partition the set of nodes in the tree, and so it could be the case that none of these are true if the left child of Y is not in the tree, and the same for the right child. So based on all of this information, that's going to determine which state we want to associate to that node Y. Specifically, which of the xi's is going to wind up containing Y. And this is based on the transition function for the particular deterministic leaf-to-root tree automaton that we're trying to turn into a formula. So for instance, if we had as part of our transition function that if the left child of a node is not part of the tree, and the right child of the node gets state 0, and the node has character A, then that node gets state 1 associated to it. We can express this as the formula saying for every Y, for every position Y, if the left child of Y is neither in state x0 or x1. Let's say we just have two states. We're implementing the odd number of A's automaton. So if the successor, if the left child of Y is neither in x0 or x1, so it's not in the tree, and the right child of Y is in x0, so we associated state x0 to it, and our node is in A, so we've associated an A to that particular node, then it necessarily has to be the case that our node is in x1. We associate the state 1 to this particular node. And so we go through all of the entries in our transition table for our automaton and translate them into corresponding formulas that express that particular transition. And that, together with these other conditions, implies that we have an accepting run encoded by the sets x0 through xm-1, where these are, m is the number of states of our deterministic tree automaton. Being able to translate any deterministic tree automaton into a formula in WS2S means that the language of WS2S is at least as expressive as the language of tree automata. But what about the reverse? If we have a particular formula in WS2S, can we translate it into a particular tree automaton? Just like this proof was, this proof is pretty much just a straightforward translation of the proof in the WS1S case. And for that proof, in order to translate WS1S formulas into word automata, we needed to expand our notion of word automata. We needed to be able to make sense of inputting multiple words at the same time into a word automaton, because we could have formulas in WS1S that talked about multiple variables. We could have formulas that have multiple free variables in them, and so they're saying something about multiple things. And so we needed to be able to input multiple things into our automata. And the procedure for doing this is exactly the same. So suppose that we had a really simple formula that had two free variables of the first type, two variables representing words, and it just said that the successor left of the first word is equal to the second word. We can translate this formula into an automaton, and that automaton is going to need to accept, for instance, a representation of the pair RRL because phi is true of RRL. Just like in the weak S1S case, we can represent first-order elements as their singletons. So we can represent the word R as a tree which has a B just at position R, so the right child of the root. And we can represent the word RL as a tree that just has a B at position RL. And then we're going to want to feed both of these tree words into our automaton that represents this particular formula here, and it should accept because this formula is true of these things. And how can we do that? Well, in the weak S1S case, we created a new alphabet consisting of pairs of elements from our alphabet and a padding character. And we could pad our words to the same length and then combine corresponding positions together into a single position that had two symbols associated to it. So let's pad these tree words to be the same, well, not length anymore, but shape. And I'm going to use this symbol here. This is a bottom symbol. And now that they're the same shape, we go through corresponding nodes and we just pair those symbols together. And now we have a tree on a larger alphabet. We needed to take pairs of elements from the original alphabet, and we also needed to include the possibility that one of those symbols was one of these bottom characters to indicate that we're past the end of one of the inputs, and we get a tree that represents our pair of inputs. So we're going to need the automaton for this particular formula to accept this particular tree word here. It's going to have a larger alphabet, and I'll let you figure out how to express this, but essentially we're just trying to say that if we look at the position of the B in the first coordinate, the left child of that node is going to have the B in the second coordinate. So this is a very straightforward thing to check with a tree automaton. So just to do another example, if we have a basic formula that says that a particular word X is contained within a set Y, we want to be able to translate that formula into a corresponding automaton, and we're going to want that automaton, for instance, to accept as a representation of the fact that the word R is in this particular set here, we're going to want it to accept the merging of these two tree words here, right? This is the tree word that we said represented R. This is the tree word that we said represented this particular set here. It has B's in all of these locations. And to merge them together, again, we extend our trees to have the same shape. We might have to extend, in both of these cases, we only had to extend one of the trees, but we might have to extend more than one of the trees, and there might actually be more than one free variable if we have a more complicated formula. But again, in this case, we only have to extend this tree with past the end of the input characters, and then we merge them together to get this tree word here, which should be accepted by our automaton for this formula because it's true of the word and set of words that this tree word represents. And really all our automaton is going to need to check is check to see that when the first character is a B, that indicates the location of the first input. The second character is also a B to indicate that that position as a word is in this set here. So another fairly straightforward thing to check with our deterministic tree automata. And just as in the weak S1S case, once you've translated the basic atomic formulas, and again, we only need to worry about the most basic atomic formulas. We don't have to worry about ones that have complicated nestings of terms because we can relationalize. Once we have automata for the basic atomic formulas, we can then recursively build up automata for more complicated formulas. Just as in the weak S1S case, we can use closure under union, intersection, and complement of regular tree languages. The proof of this is pretty much identical to the proofs for ordinary automata, to show that if particular formulas can be translated into automata, then their ands and their ors and their negations can also be translated into corresponding tree automata. And again, there's a tricky issue where you have to invoke closure under expansion if you're anding or oring together two formulas that have different sets of free variables, because you need to expand them to have the same sets of free variables before you can merge them together. It's exactly the same argument. You can prove that if a particular formula can be translated into an automaton, then there exists an X which satisfies that formula, can be translated into an automaton using, again, exactly the same argument from the weak S1S case, closure under projection. And finally, if you need to deal with a universal quantifier for all, you can just conjugate it, you can turn it into there does not exist a counterexample, and then use the arguments for not and there exists, and that's how you can turn any formula in weak S2S into a corresponding tree automaton. And again, you can do all of the things with this argument that you could do in the weak S1S case. You could take a complicated formula and translate it into an automaton and then translate it back to get an equivalent formula that was in the form of one of our automaton formulas, some sort of canonical form for weak S2S. And if we have a weak S2S sentence, that is, it doesn't have any free variables, we can translate it into an automaton that doesn't accept any input, and based on the behavior of this automaton, you can determine whether the sentence was true or false. So just like in the weak S1S case, you need to feed the automaton in the empty word on the empty language. So thanks for watching. If you have any questions or comments, please leave them down below, and be kind to each other.